Okay, so let's use one of these handy multiplication boxes, this 4-grid, to calculate some of these, quadratic kind of expressions. Okay, so let's say we have something like x and a times x plus b. Then we just do it the same way as we would with numbers. So it's x times x, which is x squared, and ax. And b times x is bx, and a times b is ab. So if you write this out long form, it's x plus a along the top, that whole width, whatever that is in this diagram, times x plus b, which is the height of the box, even though it isn't to scale. This will still be true. So we add up all the four pieces: x squared, ax, bx, and a times b. And then we write it sort of nicer by grouping terms in x. So we actually have ax plus bx, which is a plus b times x plus ab. And we notice we have kind of a product of a and b and the sum of a and b in this expression, this quadratic expression. And there are different ones we can make. So we write this nicely with some cool math. And there's other ones we can do. We can do x plus 3 times x plus 4. We can do x plus 1 times x plus 1. X plus 1 times x minus 1. X minus 1 times squared, or x minus 1 times x minus 1. We can expand that out using the same kind of diagram. Or x plus a times x minus a, which is a handy one. Or x plus a times x plus a, which is another handy one. So basically we can do this algebra by kind of using the ideas from this box multiplication. So let's just do another one just as a sort of reminder. So we've got this box here, and well, let's do this one here, x plus a times x minus a. So basically we got the box, we just write them in. So we got x plus a and x minus a, and then we do the multiplication. X times x is x squared, x times minus a is minus ax, a times x is just ax, a times minus a is just minus a squared. It was a times a to be a squared, but it's minus, so it's minus a squared. And we see that x plus a times x minus a, this thing here, equals, we add up all the terms, x squared minus ax, that's that one, ax, which is that one, a minus a squared. You've got to be careful of the minus sign. And of course these things here, this thing here and this thing here, this, sorry, it looks like a 9, but it's an a, is minus ax plus ax actually cancel out, and we're left just with these two parts, x squared and minus a squared. So that's a little handy expression. But we can always go back to this box diagram and expand them out and figure them out. Okay, so if you are given, say, this crazy quiz question, 2003 times 1997, and you don't have your calculator handy, you might guess, oh, 2003 is close to 2000, 1997 is also close to 2000, so the answer might be close to 2000 times 2000, which is 4 million. So that's a guess. I wonder if we can actually use this box thing to help us figure this out. Because we'll start with 2000 times 2000, and then we kind of correct it. So we want 2003, that part there is that side, and the other part to correct is minus 3 to get the 1997. And then when we multiply them out, it should give us the exact answer. Of course, 2000 times 2000 is 4 million, so 300, 300, so we should have 6 zeros, which is 4 million. And minus 3 times 2000 is minus 6,000, 3 zeros. Plus 3 times 2000 is plus 6,000. And minus 3 times plus 3 is minus 3 3 is 9. Okay, so far so good. So we write this out. What we actually done is 2000. So that's a 1997 part plus multiplied by the 2003 part. That's what we're doing. And actually, the parts that count are just these ones. This 6,000 and that 6,000 cancel out, which is really nice and handy. So we get the 4 million minus 9. We write that out. It's obviously that. And this is the algebra rule. This is here is the algebra rule. X plus a times x minus a. X times x minus ax plus ax minus a squared. Okay, which the ax and the minus ax cancel, and we get x squared minus a squared, which is sort of what we've done here. So, you know, it can be useful for little tricks. This is a nice one. Okay. Okay, so we can think of this expression x squared as a square box, and the sides are x wide by x high, and the area is x squared, or the number of little squares inside it is x squared. The width times the height. Pretty fine. But we can also think of it as kind of a little rule or a machine for if I give you a number x, you give me the number x squared, like a little function or a kind of calculator machine. So if we do that, we can sort of map out, okay, so what are some different x's and what are their x squared? So we can make like a little table of values. So if x is 1, x squared is 1. If x is 2, x squared is 4. If x is 3, x squared is 9. If it's minus 1 times 1 is plus 1. If it's half of a half is a quarter. So decimal is half and 0.25. If it's 1.5, then you can actually draw the square and figure it out, or use a calculator, or just know that's 2.25. If it's 2.5, it's going to be 6.25. If it's minus 2.5, it's going to be the same as plus 2.5. If it's 10 times 10 is 100. If it's minus 10 times minus 10 is also 100. If it's 0, the answer is 0. X squared is 0. And so on. So it might be handy to actually, like, instead of having these in a table format, sort of draw a picture where we have like north and south as the value of x squared, or the y-axis, and x is on the x-axis, which is sort of like the east-west axis, and we sort of draw it out as like a map, or it's called a graph. So if we go and have a look at this great little graphing calculator called Desmos. It has a calculator in it, and it also has some cool symbolic math. You can do all sorts of cool stuff. I can start just using it as a calculator. 1 times 1 is 1. 2 times 2 is 4. 1.5 squared is 2.25. A half squared, a half times a half is a quarter. 1/3 squared is 1/9. 1/10 would be 0.1, so 1/9 is a little bit bigger, 0.11111. That's just 1/9 in decimal. We can actually use this chart here, this grid paper, with some markings. There's 1, there's 2, there's 1, there's minus 1, there's minus 1 down there. We use this as the x-axis, and this is the y-axis, which is going to show us x squared. So the height of the point, we get points. We can show points by going out a certain number, then up a certain number, then draw a dot. So in this case, we go 1, 1. We go along 1, and that's x is 1. Then x squared will also be 1, and we show that as like a tuple with two parts. One is the x part, and the second part is the y part. So you go along 1 and you go up 1. Around there, let's have a look at that point. So this bracket is like bracket x, comma, y, n bracket. It's a way of showing the coordinates of a point on a map. And we could just take our table and we could mark out all these points. A half times a half is a quarter, 0.25, that looks about right. A third times a third is 1/9. So a third is about 0.3, which would be there somewhere, a little bit more. And 1/9 would be, oh, maybe there, pretty low, I think. So we draw that in. Yep, okay. 0.1, 1/10 squared is 1/100th. So 1/10 would be pretty small down here, and 100 would be a tiny amount. So we're getting close to 0 on the y-axis. 0.7 times 7 sevens are 49, so 0.7 times 0.7 is 0.49. 0.7 is 5, 6, 7, about there. And 0.49 is almost 0.5, so it's somewhere there. So we put in all these dots, and we keep going. We put in put one in there somewhere. You can sort of see it filling out this nice curve. It's not a straight line. We could join them with straight lines to show what they're doing at all the points in the middle that we haven't got. We haven't done any negative points. Okay, let's do -1. -1 times 1 is 1. Minus a half is going to be a quarter. Minus a quarter times minus a quarter is minus 4 fourths is 16, so it's plus 1/16, excuse me. So it's there. 0, of course. 0 times 0 is 0, so we'd expect a point to be there. And we could do this all day and fill out lots and lots, and it's looking sort of more like the thing. But actually, if we were to draw a nice curve through them, we'd end up with something like this. And we can get Desmos to draw these really cool lines. Look at that, x times x. So it knows that along here is x, and it's trying a whole lot of sample points, and it's drawing a whole lot of little dots and line segments and joining them up, and it draws this beautiful little graph. And of course x times x is exactly the same. That's x times x, or x squared. If we go to x, we can read off, okay, that's that one there. 1, we can read off that point there. 1.25, 1 1/4 is there. 1.5 is there. We can read off what it is. So we can find lots of other values by reading them off the graph, which is nice. Instead of writing x dot x, we could actually write x squared, because Desmos knows about squares, which is pretty cool. And we could do other functions. Instead of having x squared, we could have this other one. We could take x, we could add 1. We could take x, we could have subtract 2 from that, and then we can multiply them together, and we can get these other expressions like this. So instead of x squared, which is x times x, we could have x plus 1 times x minus 2. And Desmos has drawn that. It's pretty cool. We can zoom in and out. We can move around the graph and have a look. So if I zoom out a bit with x squared, you can see it's this sort of thing called a parabola. And if I zoom in, it's nice and curved and smooth at the bottom as it goes through 0. And if I draw this other one, this g of x, which is x plus 1 times x minus 2, a different machine, a different function, then of course I get a different graph, but it's also a parabola. It's the same kind of shape, but just moved around in different places. And a very interesting thing you'll notice is that where it crosses this graph here, well, it's called the, what do we call it? We call it the roots, actually. So g of x will be 0. In other words, the height will be 0. So it'll cross this line here, where y is 0, and x squared crosses that line right in. When x is 0, then x squared is 0. But this other function looks like it crosses the line at -1 and at 2, which is interesting. So when x is -1, then x plus 1 is 0. So when x is -1, then g of x is 0. So it crosses. When x is -1, then the g of x, this function, will give us 0. And the other place that will give us 0 is when x is, looks like 2. When x is -2, then this part here, this bracket expression, x minus 2, will be 0. And that will mean 0 times whatever is going to be 0. So g of x will be 0. So g of x is 0 at 2 points. So we see there are 2 roots to this equation here. And Desmos is just a fantastic way of graphing these things and visualizing them. So this is x squared, is the main one we've been talking about, but there are other functions. X plus 1 and x times x minus 2 is another one, and we can draw many of them using Desmos, so I highly recommend it. Okay, so if we look at another one of these quadratic expressions, x plus 3 times x plus 5, and let's draw that as one of these rectangles. Okay, x plus 3, x plus 5, so x times x is x squared, x times 3 is 3x, 5x, and 5 times 3 is 15. And if we write it out expanded form, we have x squared plus 5 plus 3x is 8x plus 15. And there's an interesting question. Can we make this rectangle here, can we actually make this something close to this expression by actually just making a full square? Can we turn this rectangle into a square somehow? So let's start with the x squared part, which is already a square. And we want to add an extra bit there and an extra bit there, which are both the same, so that we have a nice square. So that would be, those would be x. And instead of 5 and 3, we sort of want to average them out and be the same. So let's take 4, which is in the middle, and 4 and 4. So if we work this one out, we add all the pieces. So we got x squared plus 4x plus 4x plus 16. We would get in total x squared plus 8x plus 16. So this expression here is pretty close to this one. It's slightly larger. We've sort of taken this rectangle here and sort of squeezed it so that it's close to a square with the same perimeter. X plus 3 plus x plus 5 is the same as x plus 4 plus x plus 4. Because it's a square, it actually contains one more little square in the area. So let's have a look at this a little bit closer. So this one here is x plus 3 times x plus 5. And this one over here is x plus 4 times x plus 4. And we see that there's this common part. X squared plus 8x is the same in both. So that's good. It's very close. And we could write this one as x plus 4 squared. So this is actually a square, although this is a rectangle and not a square. This is actually a square, the same width and height. So we express it as a square. And over here, we notice that this thing is actually this thing minus 1. So x squared plus 8x plus 16 on the right hand side, the square is slightly larger than this one. We take away this 1 to make them actually the same. So this thing here, x plus 3 times x plus 5, is equal to x plus 4 all squared minus 1. So in other words, the rectangle area equals this box area minus 1 square. And in fact, if x were 10, as it is in this drawing, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay, in this particular case, x is 10 in this drawing. Although it's a general drawing, we could actually make x equals 10. And then this chunk here would actually be a square of 10 by 10. In other words, if x was 10, then this would be 100. If x was 10, then 3x would be 30. So we're doing one example of this special case. So we would have, on this side, we would have 13 by 15, and it would be 195. And on this side, if x was 10, then we would have 10 by 10, which is 100. 10 by 10, which is 100. And we would have 4 times 10, which is 40. And down here we would have the same, 4 times 10, which is 40, and plus the 16. And all of that together, so on this side it's 13 by 15. This rectangle is actually drawn to scale. If x was 10, it would be 13 by 15. We add up all the pieces, we get 195, 150, 180, 195. Okay, and on the right hand side, this is actually 14 by 14 when x is 10, which is the scale that I've drawn it to if one of these squares is 1. And if we add up all the pieces, 100 and 40 and 40, 180, 196. So that is actually one larger than this one. So that's pretty cool. And this idea of turning a rectangle into a square is called completing the square. And it's actually useful for other things, but this is a nice little visual introduction to it. If we go and have a look in Desmos, the wonderful graphing calculator, okay, if we have a look in Desmos, here we go. I've got some functions here that we can compare. So that's a normal x squared that I've shown. That's just a parabola. It goes through 0, 0, 1, 1, minus 1, 1. Okay, it's a simple parabola. If I look at x plus 3 times x plus 5, which is the rectangle box we've just been looking at over here, we notice that its roots are minus 3 and minus 5 when it crosses the x-axis. And if we look at x plus 4 squared, and compare it, h of x, I'm calling that, and compare it to x plus 3 times x plus 5, we'll notice they're pretty similar, but they've kind of been shifted around. So if we take that x plus 4 times x plus 4 squared, and we want to move it from here down to here, so we subtract 1, and that will, if we take x plus 4 squared and we subtract 1, we start with that and we move it down. We start with that and we move it down by 1, which is this capital F of x. Then we have the same thing as x plus 3 times x plus 5, which is what we just worked out in squares. So if we plot g of x, which is x plus 4 all squared minus 1, we get the little g of x that we're actually looking for. So and I could make this 0.5, and we would get a slightly, if it was 0.1, there's the function that we want, and there's the function we're moving. We move it a bit more, move it a bit more, move it a bit more, a bit more. And we move it into place. So you can see that this is moving the parabola around so that it actually fits this, which is exactly what we did in drawing the boxes and doing a bit of algebra in the previous section. So GeoGebra, Desmos is very, very good for exploring these kinds of things. Okay.